Okay, so in this video, we're going to go over section 2.7, which is on combining functions. So let me share my screen. Okay, so I said this is going to be section 2.7. And this is on combining or building functions given a set or collection of functions. So just with real numbers, we have these various operations on them. We want to define operations on functions because we're dealing with functions from real numbers to real numbers. So we should be able to somehow extend the operations on the real numbers to operations on functions on real numbers. So with a real number, you have addition and multiplication. And if you're interested in more advanced mathematics, this forms what's called a ring. There's a lot of different types of rings in mathematics. So a ring is just a set with two operations, usually denoted as plus and multiplication. And these two symbols right here have to satisfy various properties that you're familiar with, like commutativity of addition, associativity of addition, and then the associative property of multiplication, and then the distributive property of addition and multiplication. Although in general, in a ring, multiplication doesn't have to be commutative. So for example, all 2x2 matrices form a non-commutative ring. So multiplication of matrices is not commutative. And if you're familiar with these, matrices are basically these arrays, and you have a way of multiplying them. So you have A1, B1, C1, D1, and how you multiply them is as follows. So I'm going to take two matrices and multiply them. So you go across the row across the row and down the column. Then you do this sort of product here. This is just a rule, and you can kind of stare at it for a bit and you'll understand what's going on. And C1, B2, plus D1, D2. So you have, with the ring of matrices, you have addition, which is pretty straightforward. You just add the corresponding entries. And then you have a multiplication, which I've just defined here. And you can show that matrix multiplication is not commutative in general. So this is an example of non-commutative ring. So, but this is just a tangent. So as I was saying, we have the real numbers, we have these operations on real numbers, and we want to somehow lift or extend these operations to operations on functions of real numbers. So, and we're going to do just that. It's pretty straightforward how you do this. So let me just write down this table. So we have an algebra. This is the algebra or the arithmetics on functions or of functions. So really we just have two basic ones, adding and multiplying functions, and then the other ones can be defined in terms of it, but I'll just write all of them out. So you suppose we have some function a to the real number. So if you have two functions, f from goes from A to R. So f where A is some subset of R, and then we have another function G, which goes from B to R. And we want to define things like adding functions. So that symbol right there is not addition of numbers. If we want to be technical, it's like plus hat. So it's a different symbol. It does not represent addition of numbers. It's addition of functions. But it's going to be defined in terms of addition of numbers. So this thing, so we have this equal sign or this definition symbol. Everything on the left of the definition symbol has no meaning. And then on the right of the definition symbol, I'm going to give meaning to those uninterpreted or just these uninterpreted symbols. So addition of functions is pointwise. This is called pointwise addition. And the idea is, okay, so f plus tilde, so this f plus hat g, or tilde, or no, it's just a hat actually. We refer to this as hat. So we have this symbol plus hat. We want f plus hat g to be another function. Well, for it to be a function, we have to specify a rule. And the rule is that you take an input x, and the output of this new function, this one right here, is that you just plug it in f, plug it in g, and then add the result. And it's pretty much what you think function addition should be. But I just want to emphasize the point that you have this addition symbol here and this addition symbol here, and they're different. This addition symbol is being defined in terms of this one right here. So now we have to also specify, these are functions, so we have to specify the domain. So the domain of f plus tilde g is the intersection of a and b, because the input value has to be a value that f and g are both defined on. So and being the key word here, so that means intersection. Now we have this subtraction sign, or we have subtraction of functions, and that's also, again, we have this symbol, I'll put like a hat. So f minus g, or f minus hat g, and this subtraction symbol is different than subtraction of numbers, but I'm going to define it in terms of subtraction of numbers. So I have I have these two functions f and g. I want to define this new function f minus hat g. Well, to do that, I have to specify a rule for this function. And the rule is that you just take an input x, plug it in f, plug it in g, and then subtract g of x from f of x. So that's the rule. And again, the domain in this case will be the same as the domain above. As you can see, really, this definition right here is redundant. We don't really need this definition because the first definition kind of includes this second definition. Like addition, subtraction is really just adding a negative number, right? That's the idea. So subtracting functions is adding the negative of a function. So this definition is sort of redundant, but it might come up, so I'll just include that. So now we want one last important way of combining functions, and that is multiplication. So we have f dot hat for multiplication g. So we have this, again, it's a new function f dot hat g, and we want to build this function from the functions f and g. And again, as is the case in the two above definitions, this multiplication symbol is not the same as multiplication of numbers, but it's going to be defined in terms of multiplication on numbers. And how you do that, so we have this function, we need to specify a rule. How you define the rule associated to this function is that you take the x as your input, and you feed it through this function. And the rule of this function is that you just plug it in f, plug it in g, and then multiply those two numbers together. So again, this is pointwise subtraction. The second one, this is pointwise multiplication. I'm specifying how you multiply two functions at each point in the domain. And again, the domain of f dot hat g is equal to the intersection of a and b. Now, once I'm done writing all these definitions, I'm going to drop these hat notations, and it's just going to be assumed that when you see f plus g, that doesn't, unless f and g are themselves are numbers, but that's not going to be the case because we're always taking f and g to be functions. So whenever you see f plus g, just imagine that there's a hat over the addition sign or a hat over the multiplication sign. And that does not refer to multiplication of numbers, but multiplication of functions. So the last operation we want to define, and again, this is sort of redundant also, is division. I'm not going to put hat on this, but I'll just verbally emphasize it, that this division line right here is not division of numbers, but division of functions. And this is, so far, this is a meaningless symbol. It's uninterpreted. And now I'm going to give it meaning. And we want f over g, f bar g, to be a function itself. And for it to be a function, it has to have a rule associated to it. So the rule of this is that you plug in x in the domain. And the rule is that you plug x into f, x into g, and then you take f of x divided by g of x. And that's the rule associated to this function right here. And the domain of this is basically the same as the other ones, with one little caveat. So we have, the domain is all the x in a and b such that g of x is not 0. We don't want division by 0. So we gotta, so the domain is a little bit smaller than a intersect b, because in a intersect b, there might be points x where g is 0, but we want to exclude those points. So that's why we add this condition right here. So this is the domain of this function. So let's look at a couple examples. So this is example 1. So we have f of x f of x is 1 over x minus 2. And clearly the domain of this is any point except 2. So we had to exclude that. So the domain of this is negative infinity to 2 union 2 to infinity. And that just goes to the real numbers. We don't really care about what the range is in this case. The range will come up when we talk about what are the so-called composition of functions, which is another operation on functions that is very unlike anything you see with operations on real numbers. So the other function, g of x, is equal to the square root of x. And the domain of that is clearly 0 to infinity, and that goes to the real numbers. Again, we're not really concerned about the ranges of these functions or the images of these functions. So we want to find f plus g, f minus g, f times g, and f over g, and then we want to find their inverses. I'm not going to go through all of them. I'm just going to go through 3 of them. So we have f plus g is equal to 1 over x minus 2 plus root x. And so the domain of f plus g, according to the above definition, is the intersection of this set with this set. So we've got this intersect this. So for this so we want to figure out what this intersection is. It's not too hard to figure that out. If you take a point in the intersection, it has to be in zero. It has to be 0 to infinity, including 0, and it has to be in this set here. Well, anything that's in here is non-negative, so we got to exclude all those negative numbers. Maybe the best way to do this would be write a line. So we've got to draw the lines like we were. So we have maybe 0 here and then 2 here. So this is 0 and 2. So the top one is going to be a circle. I'm going to draw the top set as this one right here. So that will be everything here up to 2, but not including it, and then everything here. And then on the bottom set is a solid circle at 0 because we can plug 0 into the square root of x. And that's everything over here. So the intersection, we can kind of mesh these up here, is going to be this region and this region. But we have to exclude 2 from the set because although 2 is in this set, it's not in this set. So the domain of f plus g is equal to 0 to 2 union 2 to infinity. So it's all of, so let me use a different color. So it's all of this, not 2, and then the rest of this here. Subtraction is pretty trivial too. You can subtract f minus g. I'm not going to do that. And then multiplying the two functions it's not as trivial. I'll write down the multiplication. What's the product of these two functions? The domain is going to be the same. If you look back at the table I just drew above, all the domains are the same. The only difference in domain between these functions, it comes about when you look at the division of them. So the product of these two functions is as follows. And then you can just multiply numerator by numerator and denominator by denominator to get that. And the domain of that will be this also. So that's product of two functions. So I won't write down the subtraction because that's even more trivial. I just want to look at the fraction. So if you do that, what you get is the following. And you can simplify this to get 1 over x minus 2 times that. So now the domain of this, we already have some of the domain. So the domain is all the x in the intersection of those two domains, but we determine that up here. It's this right here. So all the x in the intersection of these domains, sorry, that's not right. Two union 0 to 2 union this infinity, such that g of x is not 0. So we want to determine what this set is. Well, remember g of x is square root of x, and that's 0. 0, g of x is 0 if and only if square root of x is equal to 0, if and only if x is equal to 0. So this is the point we want to exclude. Exclude from the set. from the set 0 to union 2 to infinity. So what that means is that we're just going to remove that point, and then, I'm sorry, this should be, that I made a mistake right there. So then it'll be clear that the domain is going to be 0, not including it, to 2, union 2 to infinity. So we just subtracted a, quote unquote, subtracted a point, or just plucked a point out of the set. That was the only difference. See, the only difference between this set and this set is 1 point, namely the point 0. So that's how you add these functions, multiply the functions, divide the functions, and find their respective domains. Now, the last thing I want to talk about is something quite different. It doesn't really have an analog in the world of numbers. So we started with numbers, and then we defined we started with numbers and operations on them, namely addition, subtraction, multiplication, and division. And as I said earlier, this forms what's called a ring. And then we wanted to use these operations on real numbers to extend them to operations on functions. So the idea was we want to start with two functions, f and g, and then which were functions on the real numbers, from the real numbers to the real numbers, so that you plug in a real number and you get a real number out. So we want to start with two such functions, f and g, and then find a way of building new functions from them using the arithmetic or the operations on real numbers. And we did that by defining addition of functions, which is not the exact same as addition of numbers, but it is defined in terms of addition of numbers. So we did that by adding functions, defining addition of functions, subtraction of functions, multiplication of functions, and division of functions. The next thing, and these all have like clear analogs with addition and subtraction, multiplication, division of real numbers. They're just basically defined in terms of those. They're the extension of those. So the next thing I want to talk about is composition of functions. And this is not quite like what we've seen so far, but it's not too bad. And the idea is that in those definitions I gave above about arithmetic operations on functions, they were like, you were basically applying the rule of f and g simultaneously. This composition function is, you want to apply the rule of f and g, but not simultaneously. You want to do one rule after the other. And you do this by so-called composing the functions. And this is not really something too bad. It's not something we haven't seen. So the idea is like, I think I might have brought this diagram up before, but the idea is you have two functions. So f goes a to b, g goes from, say, b to c. So notice that these match up. This is important, that these have to match up. These sets right here. So a, b, and c are all subsets of the real numbers, and you want the codomain of f to match up with the domain of g. And this will be important because you're gonna feed one function into the other in a sense. So the idea is you have an input. So functions are like these machines. I don't think I drew this actually, so I'm gonna do my best to draw the picture. Actually, why don't I just pull up the picture? Why am I drawing this? These Wacom tablets are pretty difficult to write with. So I'm going to pull up this picture right here. So our function in this case is, they took an example in the book, g of x is equal to x squared plus 1, and then f of x is equal to the square root of x. And we want to do this in sort of a fashion where we plug one function into the other. So f gets fed through g of x. G of x, g has its own rule, namely by squaring x and then adding to 1. And then we want to plug that into f and then get some sort of output. So that's the idea. Let me just write down the definition and then it'll become clear. So the setup is you have two functions, f and g. You have that f goes from the set A to the set B, and then g goes from the set B to the set C. And you have to have these sets match up for the composition of functions to make sense. So this is the codomain of f, and this is the domain of g. They have to be the same. So given these functions, the composition, and given that these sets match up, and g is, it's denoted as, as f circle g, or f compose g. The circle is red, compose. And this set, it's a function which goes from A to C now. So it's like you're almost kind of in some sense bypassing B. It's like the B, this B is in some sense, when you compose these functions, this B in some sense cancels this B. Not quite, but like you can think about it in that way if you want. So the composition of f and g is a function from A to C, and it has, again, if it's a function, it has to have some rule, and the rule is as follows: f compose g, it's a pointwise, so it's this pointwise definition. I'm defining the function at each point in the domain, and you do it simply as follows. You take g of x, you take x, you plug it in g of x, and then you plug the result of plugging x into g into f itself. So it's like you have these layers. You're layering the functions in some sense. So here's another picture. This one I can draw. It's not too bad. So you have these sets. So this is going to be B. This is going to be something that's not quite right. Okay, I did this a little bit backwards actually. This is an easy fix though. So guess the quickest, easiest way to do that is define it like this. The easiest way to fix that is as follows. So I just got to reverse it. Now, I will note, you should note that so this is going to be read as G compose F. And then let me just fix the definitions. The domains, you know, this is something you have to be really careful about. The domain, the way I had the definition set up was not quite correct because the domains didn't match. So this is even a mistake that I make still sometimes. So you got to be careful about these domains, but I can just switch the definition around and it will work. So we have a function. So this will, so the idea is that when you plug something into G compose F, it gets fed through the thing on the right first. So the X gets fed through F, and then that gets fed through G. So we want an element X to start in A because that's where F is defined. Then F will send something in A to B, and G will be defined at that. G will be defined at F of X. So how you define this is as follows. It's basically the same thing, but I just had to switch them around. So you plug in x to f of x. So f of x will be, so x is in A, so f of x is in B. And because f of x is in B, I can plug that number into G. So I get G of f of x. And then we have, I'll just bring this picture up here. So you have these, so right here is the domain. This blue set is B. Actually, now the picture's screwed up because I actually, let me just not show you this picture because it's gonna screw me up too. Because I have it defined a little differently than the book, but it's gonna, if you just follow this, you'll get the same answer. I basically just have G and F switched. So let's look at some examples. So look at examples and then we'll call it a day. So this is example 3 in the book. And you have f of x is equal to x squared. And then g of x is equal to x minus 3. So we want to find f compose g, and then g compose f. So let's do the first one. So by definition, just switching G and F around, G compose f at x will be f of g of x. So g of x is x minus 3. Now I want to plug x minus 3 into f of x. So that will be x minus 3 squared. And then g of x, or g of f of x, is g of f. So g compose f at x is equal to g of f of x. Well, f of x is x squared. And g of x is x minus 3. So I plug in wherever I see an x, I just replace that by x squared. So that'll be x squared minus 3. And in this, I won't do the whole example. In the example, they want you to find the domains, but that's not really that hard because the functions are defined everywhere. So that's not an issue. And then you can plug in some numbers, and I'll just leave that to you, or maybe we'll go over that this Friday. So that's that. That's all. There's just, you know, in sum, we have these operations on functions. We have operations that are somewhat familiar. We have the operation of adding functions, subtracting functions, multiplying functions, and dividing functions. And those are analogous. They're not the exact same thing as operations on real numbers, but they're analogous to them. They're similar to them. They're in fact, they're defined in terms of them. And then we also have this notion of composing functions, which separates the two functions in some sense. And the other one, with the arithmetic of functions, the algebra of functions, you are applying the rules simultaneously. In the composition of functions, you're doing one rule after the other. It's not simultaneous. So that's all for this section. Just I posted a homework, and it's due next Tuesday. And there's a quiz today, so don't forget that. And I will be probably releasing another video tomorrow. So that's all for now.